Hey everyone, so welcome back for an Algebra 2 semester, a Unit 2 Operations with Complex Numbers tutorial. So we're taking a kind of like a big shift from us dealing with polynomials, and then we're going to see actually within the next tutorial how we're actually relating these complex numbers. So what is a complex number? A complex number is going to have two key components. And those two components are going to be the real and the imaginary. So I like to say like, oh, we're going to be in the imaginary world, which is technically very similar to, how do I put this? You're going to see a change with a new letter, which is going to be I. And we're going to kind of step away a little bit from X. But again, we'll go ahead and jump into that in the next couple of slides. So let's go ahead and take a look at this one first. So it says match each set of numbers with the classification that best describes it. Some sets might meet the criteria for multiple classifications, so find the most specific classification for each set. So what is considered an irrational number? An irrational number is going to be a number that doesn't, it has a decimal portion to it, and the decimal part is kind of all over the place. Now, what how do we identify those types, irrational versus rational? I like to consider the types of rational numbers as like 3.33, and with this little bar, we already it represents that the 3 keeps on continuing to repeat. But say I have 3.123466153, and I'm gonna go ahead and add those dots there because it's continuing on. The thing is, there is no clear pattern there, so that actually represents our irrational number. So those are like the main difference. Real numbers are both positive and negative, and then we have integers, which is whole numbers. Another way to say it, integers are going to be whole numbers, or how do I put this? Integers, it would be considered like whole numbers. So let's go ahead and take a moment to identify working on these together. By looking at the first one right there, we have negative 227 for 1928. Do you notice that there's no decimals there? Integers, so this one I'm kind of shifting for integers only because keep in mind, integers and real numbers is like, it's that classification. They can be considered real numbers, but they can also be integers. And the reason why we're saying integers is because, again, there's no decimal there. So I'm actually going to drag this one down here to integers. Now, by taking a look at this next one here, we have the square root of 36, 1 over 6, 0.245, and negative 15. The square root of 36 is actually 6. 1 over 6 is a decimal, but it continues to repeat. So the question is this considered a real number? Or I know for sure I don't want to say it's irrational. So the question is it rational or real numbers? So by taking a look at it, real numbers can be any positive or negative numbers. So that one I'm going to actually hold off on just to make sure we can classify the other ones first, and then we'll narrow it down. So again, that one belongs to integers. So I'm going to hold off on this one for right now, but this one here, pi square root of 3 over 2, 6.283185, and then negative square root of 6. These, especially pi, is considered an irrational number. And the next one does contain pi, but again, these are decimals that are considered, or not decimals, but these are values that are considered irrational. So for rational numbers, right? Here, do you see where it's 6, 1 over 6? It's just an answer. I'm going to go ahead and actually put that in for our rational, or wait. These will be under our rational numbers because again, they don't have a, if we take 1 over 6 as a decimal, it is going to give us a repeating decimal, not like these, like irrational. And then these are going to be considered our real numbers. So it can be any number, doesn't matter if it's rational or irrational. Real numbers are both positive and negative, and those are the classifications. So a lot of these can kind of fit in between each one. But again, real numbers take both irrational and rational numbers. Integers, when specifically, is just whole numbers, both positive and negative. Let's go ahead and move on to slide 6. So think about in your head. Chances are of a number that you thought is a real number. All of the number sets you sorted in the warm up consisted of real numbers. So if you notice, like with there's that statement there, all those values are considered real numbers. So remember, in the directions they did say one of them might classify with more than one. And it turns out real numbers are the solutions to many other quadratic equations. For example, x is equal to 5 and x is equal to negative 5. They are solutions to the quadratic equation x squared equals 25. So why are we talking about a little bit of polynomials? And I said that there was like a shift because in some cases with polynomials, we're unable to solve for them. And this comes down to, they're using this example, which I'm going to also use as well, is that we can solve x squared equals 25. You isolate your x by taking the square root of both sides. Now, if you enter the square root of 25 in the calculator, you're going to just get x equals 5. But we don't just get 5. We get the positive 5 and negative 5. Now, what happens if we have x squared is equal to negative 25? And I repeat the same steps. I take the square root of x squared, take the square root of negative 25. Now, if we enter this into the calculator is going to tell you error. Although you can take the square root of x squared, which is just x, on the calculator, this is not allowed. When will it be allowed? We identify this as we can use our imaginary numbers. So, and this is why I say like they developed this new category of imaginary numbers. It's like kind of like creating its own dimension of or I like to say imaginary world, where we use the letter I. Here we cannot take, if we've been doing the algebra as we've been seeing, we cannot take the square root of negative 25. That's why here comes a shift of, what if we give you permission to go ahead and take the square root of negative 25? How would I write this? That negative is going, the negative inside the square root will actually become our I. And we already know that the square root of 25 is 5. So instead, so with that negative again during in algebra, just in general, we wouldn't even have an answer. We would just say it doesn't have a solution. So we're going to come up with this imaginary number to help us represent that negative in order for us to take the square root of negative numbers. So that's what we're going to go ahead and kind of see, just a little glimpse of what we're going to be seeing here. So what is considered a complex number? So the word complex itself sounds like it's complex, complicated, but it just contains two things. So you need a real number, and then an imaginary number. Both of them need to be combined for us to have a complex number. So here are some categories where we have real numbers, which are considered irrational numbers, and rational numbers. So again, real numbers, if you're trying to classify if a number is irrational or rational, they still fall under the category of real numbers. Now, imaginary numbers come from a negative number that's inside the square root, or as you can see here, you have 5i, 7i, and negative I will represent that negative inside the square root. So let's go ahead and take a look at that more on slide 9. So the idea is this is going to be your best friend for the rest of this tutorial. So please go ahead and make sure you take down that note. The main one I probably would like for you to make sure we get a great grasp of is I squared equals -1. I squared is going to come up a lot. And it's really nice to know that I squared always equals -1. I will be the square root of -1. So how do I relate that back to our example where we had the square root of -25? What if I rewrite the square root of -25 as the square root of -1 times 25? I'm going to break it up even more. What if I separate them? So that we take the square root of -1 times the square root of 25. Keep in mind that whole line represents the same thing that we started with. Now we follow the rule here. The first statement says that I equals the square root of -1. Here's my square root of -1. That's just I. We know that the square root of 25 is 5. It's I5, but we like to keep the I at the end, so it'd be 5I. So again, make sure you have those two lines there in your notes because that is going to help us out along the way over here. So now let's go ahead and move into slide 10. And just remember, I know it's like I tend to forget in every single video that you watch, make sure you go ahead and write notes to yourself as we work through it, especially when I'm writing on screen and working out the problems. You should go ahead and follow along and write it on paper as well. That way, when you are working on some of these questions on your own independently, you have those notes to fall back on, especially when you're moving on to doing the practice and the mastery test. So for slide 10, when people first developed numbers, they only used natural numbers and they thought they were the only kind of numbers that existed. But over time, a need arose for zero, negative values, and fractions. Each new need led to a discovery of new types of numbers, including whole numbers with zero, integers, rational numbers. Later, people found that the need of irrational numbers, so they described numbers such as the constant pi. So pi is a very famous number that is considered irrational. So the more it's like, how do we represent that there's nothing there? That was the value of zero. So they came up with zero here. How do we, I like to consider like when we're first introduced as negative numbers, right? When you're on an elevator going to the parking lot that's a parking structure that's down below, how do we represent those values? Are you on the bottom floor, which is -1 or -2 and so on, or even with money, right? When you have a bank account, you want to make sure you don't spend more than you have and not you have a negative balance. That's money that you owe. So we created a new sense of imaginary numbers in order for us to help solve for negative square roots. So many centuries after mathematicians and scientists discovered irrational numbers, they realized that there's a need to take the square root of a negative number. This now need led to the use of imaginary numbers. And I'll let you go ahead and continue on reading that. But again, this main idea, if anything, this is the main one that we like. I squared is equal to -1. What if I just want I? I isolate my I by getting rid of the square. Do you see how this is probably the first line that we wrote in that previous one? So we came up with this concept of I to help us solve for square roots that have a negative value. So let's go ahead and move on to slide 12. So by the time we found a real life use for imaginary numbers, their name had stuck. Even today, we will still refer them to as imaginary numbers. So I guess that's where they came up with the letter I. And because these numbers were called imaginary, all numbers and that weren't imaginary, both rational, irrational, or rational and irrational, got the name real numbers. Just keep in mind that imaginary numbers is just as useful as a real number. So they are gonna bring back the properties of exponents. So here's your list. You can go ahead and open up the link, take a screenshot, or again, also write your notes. The reason for this is that it's going to be super helpful, especially I'm going to be using the power of power property rule. And I will tell you why in the next example over here on slide, or it's actually a video. So go ahead and make sure you pause the video and watch the video that you see on slide 13. I'm going to continue moving forward to slide 14 here. So what we're going to go ahead and do is we're going to solve these, which they probably covered already in the video. So I'm going to go ahead and explain how I would come up with this. So they want us to expand and simplify I to raise to the 32 power. So remember the key note that I squared is equal to -1. So I'm going to take I to the 32 power. And what I'm going to do is I'm going to reformat it and or rewrite it in a sense based off of I squared. I squared can be raised to the 16th power. Now again, if we go back to the properties of exponents, this idea right here matches up to this one, a to the m power, parentheses to the n power, is you multiply n and m together. So if I multiply 16 times 32, or sorry, 2 times 16 will actually give me 32. Now I don't want to work backwards. I'm trying to simplify this, right? I don't want to have I to the 32 power. So what can I do next from here? So as long as I have the same amount of i's there, we're still good. Because remember, anything to that power, it's like saying you have I written out 32 times. That's nice. You can write it out and then you can say, oh, okay, these first two i's is -1. The next two i's is also -1. And remember, you're multiplying these values here. The thing is, it's time consuming. So the reason why we're using that power of a power property. Now, I know the value of I squared. It's -1. So I'm going to swap it out. Let me erase this. But just to get the idea of why we're minimizing some of the work here. So this is going to be -1 2 raised to the 16th power. So now anything to the 1 to any power is still going to be 1. The idea though is this negative. So the rule for the negatives is that if you have a negative raised to an even power, it will always be positive. If you have a negative that is raised to an odd power, it still remains negative. 16 is even, so we have just a positive 1 here. So I32 is equivalent to not -1, positive 1. Let's go ahead and take a look at I to the 25th power, and then I will leave you to do I to the 86 and I to the 51 on your own here. So I to the 25th power it's going to look a little bit more different compared to how we solve it. Again, you could write out all the i's out, and then for every 2 i's you write -1 and see what you're left with. But what happens if I split this? So let's just say this is raised to the 24th power plus 1. And the reason for that I'm doing that belongs to this property of product of powers property. So to be able to, I have the same base of I, but I wrote 25 as 24 plus 1. And do you see, I am working backwards. So then this is going to be I to the 24th power times I to the 1 power. Now again, we don't really like to write 1 to the 1 power. We just leave it as just I. Now, the rule that I used before for the first one is that I took this I to the 24 and I rewrote it as I squared, and I'm going to raise this to the 12th power because I know 12 times 2, right, will give me the 24. Keep in mind, I still have this I there. Now, I squared can be rewritten as -1. So I'm going to rewrite this as -1 to the 12th power. So I only replaced I squared. We multiply this by I. So -1 to the 12th power, or -1 times -1 times -1, I say that out 12 times. We know that because it's raised to an even power, it's going to be a +1 times this I, and 1 times I is just I. So I to the 25th power is equal to just I. So go ahead and do the next two following the similar methods. I to the 86 is going to be very similar to what I did there. But again, remember, I squared is equal to -1. And that idea that if you have a negative value inside and it's raised to an even power, it's going to be positive. If it's raised to an odd power, it's going to be negative. And I'm going to go ahead and move on to slide 15. So that idea of the rule that we come up with, that negative. So when we're that -1 value inside the square root becomes an I. So we could rewrite this. So they solved square root of -4 for us here. And they kind of jumped straight into it for 2i. We know what the square root of 4 is. It's 2. Take that negative and take it out as an I. But there's more work, how do I put this? It's like we're not showing all the work that comes to getting to I. And remember, that's the work that I was showing you earlier about expanding the square root of 25. So the reason for this is, yes, you can jump straight into it. It is preferred. But keep in mind, so when you have the square root of -4 is the same thing as saying -1 times 4. So the idea is that it's still under the same square root, but I'm still keeping the same values, just we have to multiply. But because we're multiplying, we can expand it. I'm going to write the square root of 4 right here and the square root of -1 over here. Or you can switch them. But we know that the square root of 4 is just 2. The square root of -1 is I, because that was one of the statements that you wrote a couple of slides ago. That's how we get to I. But the question is, do we have to show all this work? No, you can kind of jump straight into it. So if I were to ask you what is the square root of -9, you can take the square root of the number first. So the square root of 9 is 3. Don't forget that this negative can come outside of the square root as an I. So the square root of -9 is 3i. So it's very similar as if you're taking the square root. It's just when you're dealing with a negative before you were unable to solve, now you can solve. So what happens when we're dealing with a non-perfect negative square root? You can rewrite this a couple of different ways. So I have the square root of -52. And if you actually have some trouble simplifying the square roots, I will take a moment to go ahead and explain that more in depth. You can use a tree diagram to kind of help you out here. So what I can automatically do is that, oh, I noticed that there's a negative there. I can take out that negative and say, oh, it's I, and leave the square root of 52 inside. The thing is, they want you to simplify the radical as much as you can. So I know that the square root of 52 can be broken down to 52 goes in, it's 2. I'm trying to break it down with 2, but I'm thinking maybe 4 would work. Yeah. 2 is too small. So 4 goes into that 5 for 1 time. And then that's 12, that's 3. Okay. So now, why did I use 4? We know there is a list of perfect square roots that normally we start out with the square root of 1, which is just 1, right? But that doesn't really help us. I like to, we need to start out from the square root of 4, which is 2, the square root of 9, which is 3. You can see a little bit of a pattern going on there. 16 is 4. Or if you take the right side number, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And so on, right? 25, 36, 49, 64, 81, all those are perfect square roots. The idea is you look at this column and you identify which one can help you break it. But again, I wouldn't recommend using the 1 because it doesn't really help you break down the number in any way. So if I see the square root of 52, I look at my values in this yellow column here and see, all right, 52 is 52 divisible by 4? It is. 52 divided by 4 is 13. So that's why I rewrote 52 as 4 times 13. And you can double check on the calculator. If you multiply those two, you get back to the top. And the idea is you can split these. So the I is still hanging out on the outside. So you have the square root of 4 times the square root of 13. And then you know that the square root of 4 is 2. Don't forget your I. And then the square root of 13. If you notice, square root of 13 is not even listed here. It's normally between square root of 9 and 16. It's not a perfect square, so you leave it as is. Now, this still looks kind of funny, right? You would rewrite this as 2i square root 13. At least I would rewrite it that way. I know there might be, I think the Edmentum takes it like this: 2 square root 13 and the I on the outside of the square root. So we can go ahead and take a look. Yeah, so they kept it this way: 2i square root of 13. Oops. Now, what happens if you don't see it this way? There is another way. You can break this one down by using the tree diagram. Now, again, that negative represents the I. That's what I want to make sure I get the point across here. Now, how do I simplify the square root of 52? The idea is you can break 52 to, well, let's just do negative 52. We'll start out with the original. So like negative 1 times 52. We'll stop with the negative 1 because, again, it'll just be negative 1 times 1. When you're breaking these numbers, if you have to use 1, you just don't go to that extra step. If we split 52, I know that it is 2 times 20. 2 goes into 5 2 times. That's 4, 12, and then 2 and 26. 2 can be broken down to 2 and 1, but remember I said avoid the 1, so I'm going to circle the 2 and leave it there. The square root of 26 can be broken down to 2 and 13. So I'm going to stop there too. 13 can only be broken down to 13 and 1, so I'm going to stop there as well. So all those values that I circled, I'm going to put them back inside the square root as a rewritten as for negative 52. So that's negative 1 times 2 times 2 times 13. For every pair that I see for a square root, I can go ahead and take it out. So I have a pair of 2's. So I'll take it out here, a 2, and then just cross these out. Now, remember, the square root of a negative 1, that can come out as an I. There's no other 13 there. It's just one listed. So then here's your 2i square root 13. Highly suggest making sure you know your perfect square roots to go ahead and jump into this instead of using the tree diagram, because sometimes when you're dealing with a lot of larger numbers, the tree diagram can kind of get a little bit too long. But again, for square roots, you're only taking out pairs of numbers. So if you had another 13 there, you would be able to take it out. Now, if you say for a moment, you did have another 13, you would take it out and leave it out here. All this gets multiplied, just in case. But for the moment here, there was no other list of 13 pair there. You still keep it under the radical. Moving on to slide 17. So we're going to talk about the couple different ways of how to rewrite this expression. We'll go ahead and work on this one too together. So, and again, if you like the tree diagram, I'll go ahead and do the tree diagram, and then also we'll use the square root method, which I'm going to use first. So the square root of negative 27. We want to make sure which expression matches to the same answer here. So again, if I have a negative inside the square root, I can rewrite this as I and leave the square root of 27 there. And that looks like it's this one right here for us. Now, is there other ways I can rewrite this? Can I break 27 to even more down? Do you see how this I is listed inside the square root? That's wrong, right? The I comes out of the square root. So there's no need to put an I inside the square root. It always comes out. Square root of 27 is divisible by the square root of 9. So I can say that this is I times the square root of 9 times the square root of 3. Because 9 times 3, back to square root 27. Now the square root of 9 is 3. We have our I still. Then we have the square root of 3. So that first one right here is pretty, it looks good. I have an issue with this one. The I is outside, which is good, but the 9, how do we come out with a 9 here outside of it? Not possible. So this one is out as well. Here, they have a 3 on the outside, which we do here, but the inside has a square root 9. If you were to simplify this one, so 3 square root of 9i squared. Remember, I squared is represented as -1, so then you can say 3 times -9. This is 3 times the square root of 9 of -9 is 3i, which is now 9i. Again, very different from there as our answer. So it's only those two selected. But again, you just need to take it piece by piece. Another way you could have taken this is that, oh, this is 3 square root 9 times the square root of I squared. This is 3 square root of 9 is also 3. And then this square root and the square cancel, you're left with I. And then this is still 9i. So just a side example of how to simplify these, take them piece by piece, especially with the two statements that they mentioned that I asked for you to go ahead and make sure you have in your notes because it's going to come in handy. Moving on to slide 18. So complex numbers, right? The only way to identify that you have a complex number is a combination of a real number and an imaginary number. It must be written in standard form. Again, I'm going to go ahead and ask you to go ahead and write this as well. So you have your complex number, and that is considered A plus BI. Your A is your real part. BI is your imaginary. You have to have both. Both must be included. If you only have one of them, then it's not considered a complex number. So again, complex numbers contains a real part and an imaginary part. Again, make sure you have those in your notes because it comes in super handy. So here they're going to go ahead and identify a couple of different things. So like I said, for it to be considered a complex number, you must have your real and your imaginary. If you only have an imaginary number, and I can give you an example of it. So how does a complex number look like? Your real could be 3 plus 2i. Another example here could be 4 minus 6i. These two are examples of complex numbers. What happens if you don't have your real, but you have an imaginary? Then that's just saying -5i or 2i. What happens if you only have a real number? So it could be like, 3 or -10. But you don't have an imaginary, so there's no I there. Again, for it to be classified as a complex number, you must have a real and an imaginary. the both of those two values will actually be connected with either a plus sign or a negative. And again, you'll go ahead and more see a little bit more in this one. So let's go ahead and work part of this lesson activity. So starting with question number 1, match each of these powers to its equivalent. So I'll go ahead and work on one of them, and then I'll have you work on the rest. But it's very similar steps to what we saw in a question earlier about this. So I'll go ahead and go with, let me do I to the 66 power. So I to the 66 power. Again, I am going to use my information that I know of I squared equals -1. And I'm going to try to split this. So what I'm going to do here is I know 66 is divisible by 2 by 33. So this is I to the 2 power, right? The base. And I'm going to raise this to the 33rd power because I know that the rule is power, what is it called? Power of a power property. I multiply the 33 times 2 to get back to the 66. So again, just checking my work to making sure that I can go back to the original and it matches. Now I know I can replace the value of I squared with the value of -1. So I'm going to do -1 here, and I'm going to raise this to the 33 power. Now I have 1. I know it's going to be 1, but the question is, do I have a -1 or a +1? Because 33 is an odd, where that negative, we're going to have 1 negative left over. This is -1. So I to the 66 power is -1. So go ahead and do the rest of them. Here, I'll help you out with the 80, I to the 81 power. You're gonna have I to the 80 times I to the 1 power. That's equivalent to I to the 81. You focus on this on I to the 80, very similar to what I did here, using the base of I squared. And then keep in mind, you just have an I lingering around. So see if that what value you get from raising I to the 80th power. Moving on to question number 2. So they want you to identify if it's purely a real number or a non-real complex number. So some of these you're going to actually have to simplify. So for this one right here, the square root of -5 raised to the 2 power. 2 ways to do this. The square root cancels the square. You're left with -5. Now, complex number, remember, has to carry a real and an imaginary. Normally set up like this. That looks just like strictly of a real number when you're done simplifying. So again, you need to simplify this. Here's a perfect example of a non-real or complex number. So it's not just looking for specific complex numbers, you're also looking for the imaginary numbers. Remember, we're only looking for real numbers if I can get a whole number out of it. So go ahead and continue. -2 plus xi is a perfect example of a complex number. Anything, again, with an containing an I. But remember, you need to simplify it. So once you're done simplifying, if you end up still having an I there, then it's going to go under the second column. If you just get a whole number, it's going to be under the purely real number. Moving on to question number 3. So this one, we're going to go ahead and simplify. So here we have the square root of 64 plus the square root of -144. 64 can be rewritten as 8 squared, right? Because 8 squared is 64. And again, the square root and the square cancel. So you're left with the 8. Now here we have 12 squared is equivalent to 144. But remember, it needs to match up to -144. So right here, we're missing our -1. Now, it looks like here they're going to split. But remember, what is the square root of -1 equivalent to? That's what you're going to write down here. Then this, you'll cancel this to get a combination of what as your final answer here. And then again, this whole thing will be considered a complex number because it has a real, which is the 8, and your imaginary, which you're simplifying for me right there. Moving on to question number 4, part A. Says rewrite the expression as a complex number in the standard form of a plus bi. So we're going to go ahead and work on this one together. So we have 4 plus, oops, 4 plus the square root of 16 minus 4 times 5 all over 2. And that actually kind of looks like very close to what we used to do when we were not factoring but solving for polynomials. Remember, x equals negative b plus or minus b squared minus 4a times c all over 2a. It looks like our a looks like 1. And the reason I'm bringing this up because that's going to actually help you out for the next question. But let's go ahead and solve this. So remember, we break this up into little sections. I'm going to leave this 4 out here for right now. We have plus the square root of, we'll multiply that 4 and 5. So this is 16 minus 20 over 2. We'll subtract, so that is 4 plus the square root of negative 4 over 2. And because we are in imaginary, right, I like to say imaginary world, we can take the square root of negative 4. So normally when we're solving and we have a negative inside the square root, we stop and say there's no solution. But again, because you're dealing with complex numbers, you are allowed to take that value there. So we still have this 4 outside, but b plus, this will be 2i. The negative becomes the I, take the square root of 4, which is 2. I'm going to split this up here, put this over 2 and this over 2, we simplify. 4 divided by 2 is 2, plus the 2's cancel, we're left with I. So this, your complex number is 2 plus I, which you'll be typing down below. Now they're going to go ahead and say, for part B, it says in part A, you simplify the expression, the one that we just simplified down to 2 plus I. Where other types of expressions does this expression, what type of expression does this polynomial remind you of? Remember when we were dealing with the quadratic, they taught us of the quadratic formula. Identify your A, your B, and your C, and then plug it into those values, and then you'll solve for X. So it says, what concepts have you learned? So before, if we were dealing with one of the tutorials up above, if we got a negative value in here, so that's square root of negative 4, we would stop right there and say automatically no solution. But now we're allowed to say, instead of saying no solution, we can say that there's a complex solution here. So go ahead, summarize that there for part B. Don't forget to do your self-evaluation, and we will actually shift into talking about operations with complex numbers in the next video.